Okay, hello. So, so yeah, okay. Last time we mainly talked about the tensor bundles like associated to the tangent bundle. And we gave a couple examples of, such tensor bundles. Not only did we do that, we gave examples of tensor fields, sections of these tensor bundles that we do care about in physics and in other such applications. Um, and one of those places was Riemannian geometry, right? We introduced the idea of a Riemannian metric as a 2-0 tensor. Um, and we also introduced the idea of a symplectic form. Um, in the case of symplectic forms, we required that the form be closed, but we haven't discussed what that means yet. We will hopefully talk about that by the end of either today or the beginning of next meeting. Um, but first I want to like get some theory of vector fields out of the way because at the end of the day, vector fields are one of the most important um, things in physics because, for example, if you have a particle and you have some external forces, those external forces behave like vector fields on your manifold. And it's good to know like how your particle will traverse this vector field given certain initial data. So we would like to know about the flow of vector fields as we'll define today. As in like how does the particle move along the vector field? In other words, how does the particle flow along the vector field? Um, and we'll see how to take derivatives and directions of vector fields because that's what we're comfortable with from multivariable calculus. Because when we take the derivative, we always take directional derivatives. Um, and since manifold theory so far has been generalizing whatever we've seen in multivariable calculus, um, the idea remains the same here. It's okay. Um, let's start. So first, let's fix a vector field. So let X be a vector field. Um, and now one way to think about this vector field is at each point I'm giving a vector that is tangent to my space. Um, and now the question is, if I move along this vector field, let's say I was stationary, I'm being pushed along this vector field, what would my velocity vector be, right? Um, and the only suitable answer would be my velocity vector would have to correspond with the tangent vector at that point because I there's no other forces that have been applied. So there's nothing else that could be happening to me. Um, so now the question is, okay, can we always find such a curve? In other words, can we always move along a vector field? And once we answer that question, the next question will be, does this exist for all time, or are we restricted to, um, a certain time? Um, okay. So let us start at a point P, and then okay. Now we want to find a curve. Find a curve. Let's call it gamma. And this might exist for only some small amount of time. So let's just keep that this keep that in. And it has a property that we start at the point P, of course, and that our velocity at the point zero, actually at any point, not just the point zero, at any point is just the vector field at that point on the manifold. Okay. Another way to write this would be that d gamma, like the derivative of gamma, applied to d by dt at the point t equals t naught is equal to x of gamma of t. Another way to write this would be that so for all f in C infinity m, um, we have that d by dt at t equals t naught of f composed with gamma at the point t is equal to x of gamma at the point t naught. Um, this should be t naught at the point f. Okay, so these are just like, the various ways to write the derivative. That's all we've done. We've written the derivative in three different ways. Um, and and if such a curve exists, we'll say that this is an integral curve through the point P. And the reason for that is because we're sort of integrating the vector field. We're just integrating the vector. So such curve is called an integral um an integral curve of x through P. Okay. And now, okay, if we want to ask, does such a function exist? Does such a curve exist? We're gonna have to, use some theorems from maybe ODEs or PDEs. So let's see. And in this case, it'll turn out to be a theorem from ODEs, but let's build up to that. So um, let U phi be coordinates around P. Around P. Okay. And then in these coordinates, um, we can write x, the vector field x, as xi partial partial xi, right? Um, xi partial partial xi. Um, and we can write, and gamma of t is just, gamma 1 of t, so on, right? Because, I mean, this is just like, we're just writing, like, we're representing an open set of the manifold by an open set of the reals of the like of Rn. And so, we can now, instead of working in like an arbitrary manifold, we can just come back to Rn and, do things that we were comfortable with in Rn. Um, and each of these gamma i's are functions, into R. I'm doing a little, abusive notation, I guess. I'm saying that gamma composed with phi is this. I'm calling it the same thing as gamma. So this curve is not technically the right curve. We'd have to, put it back into, M. Um, okay. So, okay. Are there any questions regarding the setup so far? Okay. And now since this is just a vector valued function in R, we can just differentiate it the way we usually do, right? And then we see that gamma prime of t is nothing but gamma I prime of t partial partial xi. And what this tells you, so hence, um, now we need that this thing equals this thing at every point, okay, on the curve. So we get a system of ODEs. We get a system of ODEs given by gamma I prime of t equals xi at gamma of t. Okay. Um, but we know how to, I mean, we might not know solutions for these ODEs, but we do have an existence theorem, right? Um, so by Picard-Lindelof, we know that the solution must exist in some small neighborhood of P. Um, this implies that solution exists for some Um, Small neighborhood, P, yeah, of P. So basically, Picard-Lindelof is just saying that, we have an integral curve through the point P. Okay. Um, and the existence is, given by some epsilon. And this epsilon will work in this entire neighborhood. So hence we get a map. Hence we get a map. We get a map that I'll call phi of x that goes from negative epsilon to epsilon into v, sorry, times v into m. Here v is where the solution exists around p. So Picard-Lindelof gave us a small neighborhood in which the solution exists, and we're calling that neighborhood v, um, such that um, for any fixed q, the map um, phi x q. Um, so this map is now a curve through M. Um, right, is the integral curve, is the integral curve of x through q. Okay, does that make sense? Like like how we got such a function, um, and what this function is. Okay.
How we got it, yes, but what it is not as much.
Okay. So
It's just
okay. I think we should look back on how we got this function, and I think that might help you like figure out, what this function is doing. So, so two things happen. So one, um, we went from an open set in U, sorry, an open set in M, into an open set in Rn, and this allowed us to um, transform something about vector fields into a system of ODEs. So that's the first thing that happened. Actually, I guess three things happened. So that's the first thing that happened. We transformed from an arbitrary space into like Rn. Um, Second thing that happened is we used Picard-Lindelof to, say that the solution must exist for some small neighborhood around my point. And since phi, this map phi is a diffeomorphism, if the solution exists for a small time in P and I take the diffeomorphism, it must exist for some small neighborhood of P. So Picard-Lindelof gives us, small neighborhood of phi of P, pulling it back gets us a neighborhood of P on which the solution exists. And now since the solution exists, what you can do is on that open set of existence, we have a flow, right? For we have a flow, sorry, we have an integral curve from no, from negative epsilon to epsilon. And basically what this map phi of x is just taking all the flows and putting it as like one object. So I can fix a point P and that gives me the flow through the point P. Or what I could do is I can fix a point T and that tells me, okay, what all like where does my point go after like T seconds or like T amount of flow. So that's what this map is doing. I just explained so I wrote down fixing the point P because that gives you the flow, but you could also fix the point T and that gives you like where does everything move after T units. Does that make sense? Okay. Um, so okay, yeah, this is called the flow. Um, like the map phi is called the flow. So now in general, you only have the flow exist in some small neighborhood. right? You might not be able to say that for every point in my manifold, the flow exists for all time, right? Um, but we have a special name for if that happens. So we say X is a complete vector field if the flow at all points exists for all time. So basically what this is saying is I can start at any point in my manifold I want, and then I can flow indefinitely. I don't like blow up to infinity, for example. We'll see an example of a vector field even in R, where we have finite time blow up. Um, so since it doesn't even work in R, there's no way we can guarantee it works in any other space. Okay. Um, have you seen the like what the support of a function is? Okay, I'll just define it again. So let um, f from x into y be a function. This can be any function, doesn't have to be smooth. Um, then the support, which I'll call sup of f, is just the closure. Um, okay, so what I'm gonna write down, it'll require like some additional structure on R, and I'll like, sorry, on Y. I'll let you fit that in. Um, okay, this can be a vector space. Does it have to be a vector space? I don't know. I'll just write down the definition and then I'll let you make sense of whatever you need to make sense of. So, um, P and X, such that f of P is not zero, and then it's just a closure of that. So I guess the most general object this could be, I think, is a vector bundle. So you can take Y to be some vector bundle over X, for example. So, since I only care about whether the function is zero, we can talk about whether, like, we can talk about the support of a vector field. So in other words, like, where is the vector field non-zero? And where is there like a sequence of points where the vector field is non-zero? Yeah. So if X is a vector field, smooth vector field, um, and the support of X is compact, um, then X is complete. Okay. Um, the proof of this sort of follows from the fact that this is compact, and then you use like um, you basically break this up. You break the manifold up into like three regions, two regions. One is the support of X, and one is outside the support of X. For outside the support of X, the vector field is just zero. And since there's zero, the flow exists for all time because you're just staying where you are, you know? Uh, Very simple. Inside is where it gets, interesting because now what you have to do is you use the fact that it's compact. So every open cover has a finite subcover. And the idea now is that you have a cover of M from open sets. Um, for each point P, you have an open set on which the flow exists, right? And now, since you do this for every point, you have a open cover for the support. Now what you do is you take a finite subcover, and then you take the smallest time. Um, and then the flow will exist for this smallest time at every point, but then you just keep flowing on and on and on and on. And then you get like indefinite flow. I'll let you guys, fill in the gaps. But that's sort of the main idea. Like with a lot of these compactness proofs, it just comes down to the same thing, where you take an open cover, you find a subcover, you find a finite subcover that then allows you to, simplify whatever it is you're doing. Um, so what the main benefit of this theorem is that if we have a compact manifold, every vector field has complete flow. Okay, so this now implies that if M is compact, then every vector field has complete flow. And the reason for this is the support of any function is closed, and any closed subset of a compact Hausdorff manifold is compact. Um, Again, this is like a topology thing. I don't. It's just, for the sake of completeness. Um, but yeah, so that's one very interesting thing. Okay, like um, compact manifolds have complete flow. Um, and this should sort of make sense because if you think of the circle, for example, right? Um, it should make sense that I can't like blow up. Like it doesn't make much sense for this for like an integral curve to blow up because where is it gonna blow up to, right? The circle is bounded in some sense. Um, so okay, are there any questions about this? Okay. So now let's do some examples and then we'll talk about some more theory. So examples. Um, let's do an interesting one. So let's look at finite time blow up. Okay. So let X be uh, this vector field on R. Um, then the integral curve equation, so then an integral curve must satisfy must satisfy gamma prime equal gamma squared. Right? And this ODE is pretty straightforward. So this implies that gamma of t is nothing but 1 over c minus t, where c is just some initial condition. Um, and c is also determined by like the property that like, at the point 0, for example, uh, like where c equals 1 over gamma of 0. Um, so yeah. Uh, So now, okay, there's already a couple issues here, right? One is that the flow doesn't exist at 0, right? That the flow blows up at 0. Um, Another thing is if I am at a point where the flow exists and then I move towards the point C, the flow doesn't exist anymore because it like blows up. So so this means that like you could have like vector fields with incomplete flows, right? Um, Actually, I misspoke. At the point 0. Um, Note. So this is one thing of note. At x equals 0, uh, yeah, at x equals 0, uh, x is the 0 vector field, and so it actually has complete flow. At 0, it has complete flow. And the reason it has complete flow at 0 is because it's constant. It doesn't move. But you can never reach 0. So if you're outside of 0, you can never reach this equilibrium solution. Does that make sense? Okay. Um, let's do another example. So let's do one where there is complete flow. So let's look at uh, let x equal, x dx. Um, then I'll let you check that the integral curve um, through a point P of x is just P times e to the t. And then this tells me that the flow through x, is just P times e to the t. And this has complete flow. Um, this vector field is called the Euler vector field in R. the reason it's called the Euler vector field is because it points radially outward. And that's, like, for example, if you have a point particle with some charge, then it'll like, radiate outwards or radiate inward. This one is like radially outward. Um, I don't think that's the actual reason it's called the Euler vector field, but okay. Are there any questions about the examples and what flows are or anything like that? Okay. Um, let's now continue and let's talk more about flows. Okay. So, um, for the sake of so I'm lazy. So what I'm gonna do is I'm gonna pretend from now on that all vector fields are complete. Um, but I'll tell you exactly when we need completeness and when this holds for like a general vector field. Um, actually, do I need to do that? Uh, okay. Actually, okay. Let's not do that for now. So let x be some like let x be a vector field in M. Um, and let the flow be defined on some set. Um, okay, like the flow is defined on like let's say with flow defined on I don't know J into M, where J is like for each point P we have some set at which the flow exists. Okay. Um, does that description of J make sense? So where J is the set of all SP for which not SP, sorry, all TP where the integral curve um, through P exists at T. Okay, so we have the flow of P at the point T, through that thing. Does this make sense? Like, does this definition of J make sense? Okay. Um,
I keep
now,
forgetting I should actually say things when I.
yeah, no, that's okay. Um, so then note that um, T and phi x at s p is in J if and only if t plus s um, through the point P is in J. Moreover, phi x of t um, plus s at P is equal to phi x of t at phi x of sp. Okay. This is called the flow property. So this is called the flow property. Okay. Um, since this is such an important theorem and it doesn't like the proof isn't really that hard, we'll prove it. No proof. Um, all we really have to do is we just have to show that, um, if I fix the point S, if I fix S, um, then both these curves are integral curves through the point phi of S. Okay. And then by Picard-Lindelof and like, maximality uniqueness solutions, we get that these two things must actually be equal. And the way we do that is, we just differentiate both sides with respect to t. Um, so so what we do is consider, say, um, oh God, let f be in C infinitum. Then d by dt of f of phi x at t plus s of P is equal to, so now we do a change of variable. So d by d tau at tau equals t plus s, um, f of phi x at tau p. And then by the definition of, flow, we get that this is nothing but x at phi x. Um, sorry, this is nothing but phi of t plus s p of f. Okay. Um, but now this has shown that this is a flow. Um, yeah, I mean, this has shown that this is a flow. But the flow of this thing is, and then, sorry, one second, I just lost my train of thought completely. Yeah, so we've shown that this thing is the flow, and then this the fact that this is the flow of this is by definition. Like this is quite literally the definition of the flow of like for time t through this point. What this means is hence by uniqueness, f of t plus s at p is equal to um yeah, because another way you can so another way to see this is you can write this as actually no, that's the only way really. X t plus s p of f. And yeah, so by uniqueness we get this. Um, and then this is the main property, and then this fact just holds because this equality holds, and we've just shifted the flow by s. Um, yeah, so does that make sense? Okay. Um, okay. One thing to now note, right? So one thing to note is that phi x of 0 to p is just p, right? Because that's where we start. This implies that phi x of how do I want to write this? Phi x, let's write it like that. Phi x at 0 is the identity function on M. Okay. Um, Hence phi phi of tx is a diffeomorphism. Okay. Is a diffeomorphism of its domain. The reason it's a diffeomorphism is because since phi minus tx is its inverse. And I'll let you check why this exists and why, you know, these two are inverses of each other. Um, okay, so if you have a collection of, functions that are parameterized by t, by some parameter t, you can check very clearly if, this family of functions is supposed to be a flow, by checking that if I compose them, it's the same thing as if I add. Um, what this means now is that if X is complete, we get we get a smooth action. of F, sorry, of R on M.
Okay, wait, now that I've been like looking at it more,
Yeah.
you just kind of say since phi is its inverse. Is that like part of, is that why it's a diffeomorphism, or are
Yeah,
we
so
doing things now like because there are two periods? I don't know which.
yeah, so okay, so I'm saying that the flow at point zero is the identity function. Yeah. And now if I look at the flow at some time t, so I fix the time t and I'm looking at, all the points, like where do all the points get pushed? Well, do all the points get pushed? I'm claiming that this is a diffeomorphism. So we have to check a couple of things, right? So we have to check that it's smooth. We have to check that it's bijective. And then we have to check that its inverse is smooth. We know this thing is smooth by definition, because this has to be smooth, from Picard-Lindelof. Um, and then we're saying, instead of like, showing that it's the diffeomorphism, we can just check that it has an inverse. Right? And its inverse is if I just, went backwards. So if I take everything and instead of going forwards, I go backwards. So
So
that's what
it's
it
that
is.
it's a diffeomorphism since this is its inverse.
Yeah, yeah,
Okay.
yeah. And then its inverse is also smooth. That's another important thing we have to mention. Okay, so X is complete. So if X is complete, we get a smooth action of R on M. And the way the smooth action is given is, you send T to the flow of X at the point T. Um, and one interesting thing to note is that not only not only are these functions diffeomorphisms, they must commute with each other because, it commutes here. So, and we have a group homomorphism into the diffeomorphism group of M. Um, so another way to say this is like the flows of complete vector fields are in the center of the group of diffeomorphisms. And this is like, I don't know. I think it's pretty cool. It's not really that important to really, it's not that important, but it's just an important observation. And we do need the fact that the flow is complete for this because as we saw before, we might not have flow at the time t. And so we can't compose things. So we do require complete flows. Okay. Um, yeah, are there any questions on this? On like this group action that we have? Okay. Um, so let me see, what else do we have? Yeah, so let's now, I think I should, hmm. Let's now talk about the Lie bracket. So, yep. Say let X and Y be vector fields. Um, um, and now the question is, how do we like make new vector fields out of this vector fields? Um, we I mean, it's pretty obvious by looking at vector fields as sections of a certain vector bundle that linear combinations of these will also be, um, you know, sections of the same vector bundle and hence will be vector fields. But another way we can think of a vector field is as functions, right? Because that's how we saw it initially. We saw them as like at each point we like take the derivative in the direction of x. Um, and now the question is, okay, can I compose these like functions and still get a vector field? So is um is x compose y a vector field? And the answer is no, right? Let's check this quickly. So let f be C infinity m, then x compose y f. If we write this in local coordinates, um, we get that this is xi partial I, yj partial j f, and then we use product rule. So we get xi partial I, yj partial j f plus xi partial j, sorry, xi yj partial I partial j. So this is clearly not a vector field because this is a second order derivative. And we can also see using the fact that, these partial derivatives commute for smooth functions, we can see that if I flip them, so if I look at y compose f, um, I get the exact same thing. So let me just write this down quickly. Partial I x partial j f yi partial I xj partial j f plus xi, sorry, xj yi partial I partial j f. And now if we swap I and j, since we're summing over them, this term and this term are exactly the same. So we can just cancel them out if we subtract. Hence, the commutator, like the Lie bracket, equals x, y, f minus y, x, f is a vector field.
I had a question about that. So in ODEs, you can look at like a second order ODE as a system of differential equations.
Mhm.
So you said that this is not a vector field since there's a second derivative, but could we see it as a vector field if we did like a system of first order derivatives? And is
Yeah,
that
so
useful?
so you can look at it. So when you do the like system of ODEs, what you're doing is you're taking this vector field defined on the manifold and pushing it up to a vector field defined on the tangent bundle.
Okay.
So yeah, in some sense, like that's a good way of looking at it, where like sure, it's not a vector field on the manifold itself, but it's a vector field on a tangent bundle, right? Because in that case now, these things would now be coordinates on your space, right? So
Right.
now it's just like coordinates rather than derivatives. If
Okay.
you've done like Lagrangian mechanics, this is basically like what you do, right? Because you have some action defined on the tangent bundle, and then you take like an associated vector field, and then you solve the ODEs, and that's a second order differential equation. So that's exactly what we're doing here. So that's exactly the question you've asked. It's sure you can look at second order ODEs as, flows on tangent bundles. Yeah. But yeah, in our case, we only care about, vector fields on the base manifold. Um, so yeah, so in that case, like since we care about like the base manifold itself, we don't allow second order derivatives at all because they don't satisfy Leibniz rule. Um, and hence the like this commutator is a vector field, and we'll call this the Lie derivative, or like sorry, the Lie bracket. So this is the Lie bracket of x and y. Okay. So okay, that's good. Now we're gonna do something a little, um, a little weird, I must admit. Um, and we're gonna try to, move around some vector fields. We're gonna try to move around some vector fields. Um, so suppose we have a diffeomorphism. Suppose F is a diffeomorphism. Um, then we saw that we can take smooth functions on, I guess I didn't really mention from where to where. From M into N. One second. Yeah. So we saw that we can take smooth functions on M and transform them to smooth functions on M by taking pullbacks. Sorry, I said that the other way around. We can take smooth functions on M, sorry, on N, and make them smooth functions on M by taking the pullback. Um, so, you know, um, is a function from M into R given by P goes to F of FP. And one thing to note is that since F is a diffeomorphism, every smooth function on M is a smooth function on N that has been pulled back. That has been pulled back. And now the question is, okay, can we do something similar with vector fields? Right? Is there something similar that we can do with vector fields? And the answer is yes. Um, I've defined sorry, one second. Um, in the problem sheet, like I've talked more about the pullback of vector fields. So I'll just give you like the naive definition at this point, which I've also defined um, in the problem sheet. And the idea is we're just going to, at each point, all we're going to do is we're going to pull back the function, differentiate it, and then say that's our new vector field. So let X be a vector field on N, then we define um, the vector field Y on, so this should be on M by um, Y of P, so at the point P, is just the pullback. It's basically the pullback by, or rather the push forward by the derivative. Um, so it's going to be the derivative of, sorry, I have it wrong in my notes, I just realized. Um, hmm, okay. I'm trying to see if I want to define it this way. I think for our situation, it'll be easier if I define it this way. Um, so we have C infinity M, right? Over here, we have C infinity N. And now we saw that the pullback, defines a map that takes, smooth functions on N into smooth functions on M. A vector field Y on N is now a map that takes smooth functions on N and gives you another smooth function on N. Okay. And now we can do the same pullback nonsense up here and get smooth function on M. Since F is a diffeomorphism, we can actually complete this diagram, okay, to get a vector field F, sorry, we can complete this diagram to get a vector field on M that we will call the pullback of Y. Okay. And then this is like a commutative diagram. Okay. Does this definition make sense? You seem unsure. So if there's anything about this, because this is a very, very, very important definition. So if it doesn't make sense, please let me know.
Oh, I need more time to look at the commutative diagram 'cause it's
Okay.
a
Do you want me to
lot to take
explain it
in.
again? Do you think?
Um, I think what is confusing me right now is
Mhm.
that you can so you can get from like C infinity n to C infinity m by F, is that F dual
Yeah,
P
so
star?
it's this map
But
over here.
then right, but and then the other same thing on the other side.
Yeah.
But then also you can, oh no, never mind. I
Let,
think I get it.
let me write it this way. Maybe that might help, like, I don't know, mentally. So this arrow just means there exists such a morphism.
Okay.
Um, but yeah, I mean the idea is simple, right? Like the way I'm gonna define the pullback vector field is I'll define it on the pullback of functions. But since f is a diffeomorphism, every function is the pullback of some other function. And so in that case, it make I can just, I can just define it on the pullback. And so the idea is that I can get from C infinity n into C infinity m in two ways using the vector field and the pullback. I could first take the pullback and then move over by some vector field, or I could first apply my vector field and then pull back. So in more like if I wrote out this definition, what this is saying is that the pullback vector field on the pullback of some function g has the same action as if I took, y, applied it to g, and then I pulled that back. Okay. Um, or in other words, the pullback. So in, concretely, the pullback is just defined by taking the derivative of f inverse at the point P and applying it to y. So this should be f of P. Because this is a diffeomorphism, I can take the pullback, I can take the derivative and, you know, um, I can take the derivative of the inverse and then apply the vector field at that point. Maybe this definition might help. But it turns out like this commutative diagram actually gives you all the information you need about the vector field. Um, so in the exercises in the problem sheet, I've asked you to prove something like a similar property. And that's basically we'll now make use of the fact that if I take the pullback of the, of xy, this is the same thing as taking the commutator of the pullbacks. And I've outlined the proof in the problem sheet. So we'll just take this as a given. Are there any questions about this? Okay. Um, yeah, so this is outlined in the problem.
I'm muted. I just realized the notation, so are we evaluating the derivative at P and then applying it to
Over here.
yes.
Okay, so
I don't know if you used that somewhere else already
okay,
or
so let me write this down, right? So uh f takes a point P into f of P,
hmm
right? And moreover, it takes the tangent space at M into the tangent space of f of P in N,
Okay.
right? So f inverse will now take f of P and map you into P,
hmm
and it'll take the tangent space at f of P at N into the tangent space at P of M.
hmm
What this now means is that the derivative of f inverse has to be evaluated at the point f of P.
Okay.
And hence it takes tangent vectors at f of P in N.
Okay.
So that's what I'm doing here. And now remember, y was a vector field on N. And so I can evaluate this at the vector field at the point f of P.
Okay. Just making sure that that was
No.
what was happening.
Yeah, thank you for asking. Um, okay, so this I've outlined the proof of this in the exercises as I've said. Um, but yeah, this is a very important result that we will now make use of. So we're going to note the following, right? So um, if you have some like vector field, so let um, let X be some vector field. Not necessarily complete. Okay. Um, this means actually wait, I should be a little more careful with how I say this. Okay, so let X be complete for now. Um, be complete. So then we get a flow. We have some flow map, right? We have 5x at the point t, and this is like the flow at some time t. But this is a diffeomorphism. So what this means is I can take like the pullback map, right? Um, that induces like that I can take like vector fields on M and get new vector fields on M by, taking Y and then taking the pullback at Y. Okay. So I don't really know how to like explain this. So you have some flow, it pushes everything forward a little bit in the direction of X, and then you're like pulling it back, you're pulling Y back. And now the idea is that if I take the derivative at 0, I'm basically saying, okay, if I move just a little bit in the direction of X, right? Um, how much does Y change? Right? Um, and so we get two maps. So we get a map like this. Um, that works on functions by, same thing. We take the derivative at t equals 0 of phi x t pullback of f. This one is nicer, but I mean, this one is easier to wrap your head around because it's like clearly if I'm moving in the direction of x and I'm looking at, what like the derivative of the function as I move in the direction of x, like what is that? Um, and like that. So this is called the Lie derivative. Oh my God, this is called the Lie derivative of f with respect to x. Okay, so it's basically the directional derivative of f in the direction of x. But now we can also do this for vector fields, right? Um, so let's do that. So x at y is just the same thing, d by dt, t equals 0, and then now you just pull back the vector field itself. Okay. This one is like a lot more difficult, at least for me, to wrap my head around this. I, with a lot of these things, I would honestly just recommend, working out a couple examples, very simple ones, to see if you can compute the Lie derivative of them directly. Um, but why am I introducing this? So one, this now gives us a way of measuring how much y changes in the direction of x, right? I mean, like that's very important. Another thing is we'll see that this thing actually has a very nice expression that we can evaluate. So um, okay, so proposition, actually theorem, and I think this is where we might have to call it for today, like after we prove this. Um, so let x and y be vector fields on M, not necessarily complete, because this definition makes sense. Um, like both of these definitions make sense even when X is not complete because the flow exists for small enough time, right? At every point. Um, and that's all we really care about. Um, so let X and Y be vector fields. Then the Lie derivative of Y with respect to X is just equal to the Lie bracket of X and Y. Proof? Okay. So what we're gonna do is, I mean, we're just gonna take derivatives of things and we're gonna see that um, both of these satisfy like both of these give us something, and then we, yeah. So note that phi at this pullback of y of f. Remember our commutative diagram up here. This is just equal to the pullback of you know, is just equal to the pullback of the vector field applied to the pullback of the function. So this is nothing but the pullback. Um, sorry, this is nothing but the pullback of the vector field applied to the pullback of the function. Okay. And now what we're going to do is we're going to differentiate at t equals 0. Now take derivative at t equals 0. And what do we get? So this thing, by the definition of a flow, this thing just gives you x evaluated at the point y of f. Okay. And now we have to do, a product, sorry, like it's like chain rule, product rule. Um, to get d by dt at t equals 0 of the pullback um, at y evaluated at f plus y times d by dt at t equals 0. Yeah, so this is like product rule. Um, d by dt of the pullback of the function. But note, right, by the definition of the Lie derivative, um, this is just the Lie derivative of x evaluate the function y, and then this is just y of x of f. And with this now just subtracting, we get that the Lie derivative is just the Lie bracket. Okay. One final thing that I'll mention is that note that the Lie derivative of x in the direction of y is equal to negative the Lie derivative of x. Sorry, the Lie derivative of y in the direction x is negative the Lie derivative of x in the direction y. Um, which would have been very non-trivial to see without, without this. So, okay, are there any questions on anything we've talked about today? No? If not, I will see you guys on Tuesday. Um, and yeah.